In today's show, we hear about the materials that are not just solids or liquids or gases, but they're all three in one. Well, not so mysteriously, the soil under your feet is one such material. Of course, a solid with air and water mixed in.
And knowing how soil behaves is especially helpful when you intend to build on it. And how soil behaves is even more interesting when you're trying to build on top of land that might be hit by an earthquake.
You're listening to The Science Show on Cambridge 105.
In this section called Scientists at Work, we talk to people who, for some reason or another, find themselves working, researching or thinking about science in Cambridge, England. Dr. Mark Haw will be telling us just how important are the physical properties of materials. We'll hear about his work in fluid physics and chemical and process engineering. Well, Dr. Mark Haw from the University of Strathclyde lectures about multi-phase systems and also the flow response of suspensions and granular media. You'd be forgiven for not connecting any of that with something we learned at school, but he'll be explaining today that his branch of engineering, like so many areas of research today, is actually a mix of all those subjects.
And we met Dr. Haw when he came down from Glasgow to Cambridge. He was here to give a talk at the Science Festival about what life really is and what it's made of. Thinking of the fictional Dr. Frankenstein, how do we go from a body made of sewed-together parts to a living thing? Dr. Haw talks about this in his chat with Roger.
OK, well, let's listen to the recording. It lasts 10 or so minutes.
So I'm a lecturer at the University of Strathclyde, and I'm in the Department of Chemical and Process Engineering. So chemical engineering is all about how do we make a lot of the products we rely on in everyday life. So if you think of anything from, obviously, petrol that goes in your car, right through to the cornflakes you have for breakfast, all of these things have to be made, they have to be processed, and they have to be made on a certain scale, which is the scale that people want to use them, whether it's a lot of petrol that people use or whether it's a relatively small amount of cornflakes, but nevertheless you make a lot of profit out of cornflakes, so it's quite an important kind of area, food science. So that's kind of what I do every day, but my background is not really as a chemical engineer, my background is actually as a physicist. And what I find probably most interesting about what I do every day is that it's not really just chemistry or physics or engineering, it's all of those. It's trying to put all of those things together to end up with these products that everybody relies on every day, and also some of the kind of really fundamental science underlying a lot of the stuff we rely on in our kind of modern world.
OK, so what would work look like?
I mean, in the lab, for example, one of the things we try and study is how do materials that are not simple liquids or gases or solids, but are some mixture of those materials, how do those materials behave? For example, if you make a material flow by applying a pressure to it, if it's a simple liquid, we kind of understand how that works, and there are even fundamental theories to tell us how that should work. And that's what things like aeroplanes are based on. That's why we can build aeroplanes and we can fly them relatively safely. But actually a lot of materials are not just liquids or gases or solids, they're mixtures of all these things. So examples are all around us, like soil. The stuff we walk on is not just a solid, it's also got water in it, it's got potentially gases in it, so lots of it's kind of a porous material with a mixture of these phases. Now, you might think, well, that's okay, but who cares? You know, we know what soil does. But of course, when you build a building, you have to do a lot of preparation to the ground to make sure that building is going to stay up. And we see quite often what happens when things go wrong. So, for example, when there's an earthquake is applying an enormous force to the soil. Now, people can design buildings that could withstand that force, and that's exactly what they do in places like Japan that have a lot of earthquakes. But what is much more difficult is designing how you make the soil withstand those forces. And so we see situations such as a couple of years ago, there was a big earthquake in Christchurch in New Zealand, and it caused an enormous amount of damage. And it wasn't because the buildings couldn't withstand the forces, it was because the soil that they were built on, it should have been a solid, but it turned into a liquid under the effect of these forces. It flowed, so the buildings fell over. And that actually is quite close to home in a sense for us, because one of the big areas that was destroyed was large parts of the university in Christchurch, including the chemical engineering department. So we've had a certain amount of communication with our kind of fellow chemical engineers over there, essentially saying, can we do anything to help out? So those sort of things are actually really important in everyday life, but these mixtures of liquids, solids, gases, it's much more difficult to know how they're going to behave. And so that's one of the things we try and study. For instance, when you extract oil and gas from under the North Sea, nowadays it's getting more and more difficult because instead of going for the easy oil wells that are just oil, nowadays they're going for the wells that are actually a large amount of water as well, and quite often sand. So you've got this mixture of solids, sand, and different liquids that don't really want to mix. And they behave differently then when you try and extract them out of under the seabed and you try and pump them back to shore or back to your refinery. Now, we don't go there and do that, although some of our students do. A lot of our students end up working in that industry. But in terms of research, what we do is try and study those sort of materials, but in the lab where we can really see what's going on. You can imagine if you're at the bottom of the North Sea, you can't really see what's going on. It's not an easy place to do research. But we can research in the lab on these similar sorts of materials to try and learn about the fundamentals of how they behave. And then hopefully we can talk to the people in the oil industries and say, look, if you do this, if you have this sort of problem, that's probably because your material is doing this. And if you change the process somehow, that may improve the process and it may make it more reliable. And that's one of our goals. And this, again, is like a lot of scientific work in universities. It's doing the research that you can then apply to outside processes. You're trying to get at the fundamentals which could then be applied to the applications actually, making materials or making products.
So that sounds like you're servicing civil engineers, does it not?
To a certain extent, and this is what I mean when I say I don't really do engineering or physics or chemistry all on their own. I do them kind of thrown together. And actually this is much more common in science and engineering, that we all work together. So there are still these barriers between the disciplines. But in reality, if you become an engineer or a physicist or a chemist, you could easily end up working alongside people from completely different disciplines. And of course, the really interesting area now as well for chemists and physicists is now starting to work on biology, trying to understand the kind of chemistry and physics that underlines living things. So rather than just map out what living things do, try and understand, well, how is it that the chemical behaviour of, say, the DNA or the proteins, the molecules that are inside us, how is it that chemical and physical behaviour leads to what living systems can achieve, which is generally much more clever and complex than anything else that we could build ourselves at the moment.
Okay, so you're a colloid of subjects.
Yes, exactly. A big mixture. But, I think one of the important things that anybody thinking about science careers nowadays perhaps doesn't realise when you look at school and when you look at university, you see these separate subjects, but actually most of us are working somewhere around the borders between subjects. And so you have to be ready to be able to talk other people's languages, to be able to think about other concepts from different directions, and to be able to communicate your own view of things in a way that helps people understand where you're coming from as well.
Give an example of a measurement that you might need to make.
Well, really simple measurements, which sound really simple, but for example, if you apply a certain pressure to a liquid, how fast does it flow? Because in a chemical process, you're often transporting liquids from one place to another, and mixtures of liquids and solids, as I said. And you need to know how much force do I need to use. If I want material to come out at the end of a pipe at a certain rate, so that it goes into, say, a chemical reactor at the right rate, so we can produce the product at the right rate, how much force do I need to use to make that flow? So that's a really simple kind of measurement. And in principle, that's the sort of measurement that happens all the time. But as I said, once you get much more complex materials where you have mixtures of different phases, solids, liquids, gases, this becomes much more difficult. And then you find that these materials, they don't even behave kind of consistently over time. You might apply a certain pressure and it flows at a certain rate, but then it decides, because it's full of solids that get stuck, it then decides, no, I'm not going to flow anymore. And so you then try and make it flow by pushing harder, by increasing the pressure. But what you find, and one of the research areas we do a lot of, is that if you do that, all you really do is apply more force to the kind of pipe that you're trying to flow in. So you're actually more likely just to make everything explode. So applying more force, although it seems like the obvious thing to do, doesn't actually do what you want it to. So there's an example where normal liquid would behave exactly like that, seems very simple, but once you have one of these more complex materials, it often behaves the opposite way to what you expect, and you need to know that.
Okay. Can you think of a unit that comes out of that?
The obvious units are how much material is flowing per unit time. So you might have a volume or a mass of material, depending on how you want to measure it, per unit time. Or the unit of force might be actually the unit of pressure. So how much force are you applying per unit area? If you have a pipe that has a certain area, and you're applying that force over that area, that gives you a pressure.
Okay.
So these are very simple units that find out about at school, but actually they are real things that people are measuring all the time and trying to control for people to end up with all those products they need every day.
Okay, you've almost answered my next question, which was to ask what bit of school crops up most often?
So temperature is one of the variables that will determine how a material behaves. Mm-hmm. And quite often, in a simple way, you might think, well, the important thing about temperature is it going to melt something? So you might start off with ice, and if you go to a temperature above 0 degrees C, it melts, it turns into water, and they obviously ice and water are very different. So that, in that sense, temperature is important. But in lots of other ways, perhaps more complex ways, temperature is important. I remember doing an experiment. This really came home to me. I remember this at school. It's probably the only experiment I remember doing at school because I got it wrong. You always remember the ones you get wrong. And I remember we were trying to measure how much energy did you need to heat up some oil. So we were applying energy by heating up this oil using a Bunsen burner, using a flame. I don't think they'd let you do it these days. It's probably slightly dangerous.
Yeah.
And we were measuring the temperature. So we just had a thermometer sitting in this bowl of oil. But the thing which I didn't think of is that you're applying the heat to this oil, but the heat is taking a while to kind of spread out around in the oil. So you're getting a hot bit right where the flame is, and actually a much cooler bit a long way away from the flame, because the heat has to spend time moving and diffusing out through the material. So what I should have been doing to measure the temperature accurately is I should have been stirring all the time to help the heat move around. Of course, I was lazy. I thought, I can't be bothered to stir. I'll go and do something else while this is doing, and then I'll come back and I'll measure the temperature. And when I measured the temperature, I thought, well, that's not very warm, so I'll keep going. And eventually I realised, I should be stirring. I tried stirring, and it turned out the temperature was much, much higher than I realised because I hadn't stirred, and all the heat had just stayed concentrated in one place. So it was actually, in a way, useful because it ended happily, nothing exploded. But it was useful to make a mistake like that because it's what makes you realise, it really gets those ideas into your head. The way heat moves around, it makes you realise just how important it is to think about how materials behave if you're going to try and do something with them.
Excellent. Now, you're here in Cambridge to give us a talk trying to create a Frankenstein. So can you, for the people who might have missed it, give us a quick...
Yeah, the idea behind this talk is that, as I said, one of the things that chemists and physicists are getting really interested in now is understanding how does chemistry and physics lead to the kind of behaviour that living systems display. And living systems are much more complex than anything we've really dealt with before. But it's in the last 20 years or so, we're getting techniques now where we can really measure what the molecules are doing inside cells. And we're all made out of cells, and those cells are full of molecules. And those molecules are doing more than just chemical reaction like in a test tube. They're doing constant processes. This is a bit back to chemical engineering. It's processes where materials are coming into the cell, they're being turned into other materials, those materials are being used in a next reaction to be turned into something else and turned into some... And the whole thing works in this complicated process that's constantly drawing in food and energy and making whatever the cell needs to survive. And we're starting to understand how that works. Now, 200 years, almost exactly 200 years ago, Mary Shelley obviously had a dream, and this led to her story, Frankenstein, where she was thinking really along exactly the same lines. How do you go from something that's essentially just a bag of chemicals to something that's a living being? And of course, at that time, really, people knew very little about molecules and atoms and so on and energy. So there was not really anywhere you could go with it. I suppose my point now is that we actually have techniques where we can start to answer that question very precisely, and not just in a sort of chemistry way, but in a physics way as well, of thinking about how the molecules inside us move around to achieve what they need to achieve in order to carry out all these processes that produce all the other chemicals that are needed to keep the cell going. So we now have techniques to do that, and my contention, and this is something that I'm going to kind of put out there for the audience to think about, is in probably 20 or 30 years we will be in a position to more or less be able to say we've filled in this gap between that bag of inanimate chemicals and a living thing. We've actually filled it in with science, which we can't really do yet, but over the next 20 or 30 years, I think we will essentially answer that question, how does life work? And so what I'm going to talk about is various of the attempts people have made so far to answer that question. I'm also going to talk about what I think are the consequences of this. Now, Mary Shelley's book was really about consequences. It wasn't about the science. There wasn't enough science there for people to really understand at the time. It was about perhaps the social consequences of what might happen if somebody could actually make a living being. And actually those consequences are the same now, except that now we may have to actually really start to deal with them because we may actually be able to do this in the next 20 to 30 years.
And so it's not about jump leads?
Not as far as I'm aware. I don't think that's likely to be the answer, and hopefully I'll convince people that's probably not the answer.
That's pretty much all for today's show. Scientists at Work is made by the Science Show team on Community Radio Cambridge 105. You can also find past episodes on the website www.cambridge105.fm. You can also subscribe to future podcasts with the iTunes Store. You can get in touch with us on the email science@cambridge105.fm or on Twitter @105science. Till next time, it's bye from the Science Show team of Roger Frost and Chris Crease.
You're listening to The Science Show on Cambridge 105.